Dear students, in this module we will continue the study to the carbon-carbon multiple bonds and we will deal with the conjugated addition reaction, which is Michael addition. And we will also study in this module about how the addition happens in cyclopropane ring. And you must be wondering why cyclopropane ring comes in this section. We will see how, because of the strain, the cyclopropane ring, although saturated, behaves like a double bond and it will be undergoing addition just similar to the other CC double bond addition reaction that you are familiar and we will be studying further. So, dear students, after studying this module, you shall be able to know about the Michael conjugate addition reaction, learn about the Michael acceptors and donors used for the reaction, familiarize yourself with the mechanistic aspects of Michael reaction. You will be able to acquire an understanding about the asymmetric variants of Michael reaction and identify the reason for enhanced reactivity of cyclopropane ring and the various types of addition that cyclopropane systems undergo. So, dear students, let us begin with the Michael reaction. Now, if we try to know what is Michael reaction, the Michael reaction can be understood as a base catalyzed 1,4 conjugate addition of an activated methylene, which is termed as Michael donor, with a conjugated olefin, which is known as Michael acceptor, as you can see in this equation. So, here you can see that there is a methylene group joined to two electron withdrawing groups, in general represented here by EWG, and it reacts with Michael acceptor, which is a conjugated carbonyl, and you can see here the 1, 2, 3, 4 numbering, and it is relatively at the 1,4 where the addition will happen. So, as these two react in the presence of base, we get this 1,4 addition product, which further reacts with proton and gives you this enol, and this enol will be tautomerizing into the corresponding keto form. So, that will be appearing as the 3,4 addition product. The activated methylene, that is the methylene donor, is a methylene group which is bonded to two electron withdrawing groups. These two groups can be same or different. The electron withdrawing groups help in stabilizing the negative charge that forms after the removal of proton from the methylene group by the base. Thus, the various functionalities like aldehydes, ketones, diketones, esters, diesters, ketoesters, carboxylic acids, dicarboxylic acids, nitriles and nitro compounds can act as efficient Michael donors. Initially, the Michael reaction was done with an alpha beta unsaturated carbonyl compound, that is Michael acceptor only. Later it was extended to a variety of substrates including esters, nitriles, sulfones and compounds with activated double bonds like alkyl acrylates, vinyl ketones, acrylonitrile, etc. So, all you can see here, the various electron withdrawing groups are represented, and you are also shown here the various Michael donors. You can see here it is a CH2 joined to 2 COOET, or you have one ketone and one ester, or you have two cyano groups, and then you are shown here the Michael acceptors, and in all of them you can see there is a double bond which is conjugated with either you have a ketone in first case, in the other the double bond is conjugated to cyano, then you have this conjugated to the ester group, and in this one the double bond is conjugated to two ester groups. So, all these are the Michael acceptors. The conjugation of a double bond to a carbonyl group due to resonance exhibits the electrophilic or electron deficient character to the beta carbon of the double bond. It is due to this that the nucleophile may easily react with this and result in the formation of 1,4 addition product. A strong base is used to generate the enolate, which acts as a nucleophile from the Michael donor, and the commonly used bases in the reaction are alkoxides, sodium hydroxide, potassium hydroxide, LDA, etc. in the presence of protic solvents like alcohols. For example, as you can see in this equation shown, the two electron withdrawing ester groups in diethyl malonate help the methylene group to act as Michael donor. On the other hand, the second molecule shown here acts as Michael acceptor, where you can see the phenyl and ester group are attached to the double bond and they help the addition of Michael donor to the Michael acceptor. And once these two combine, this combination is happening in the presence of base. For example, here it is sodium ethoxide, and followed by acid workup, there will be formation of enol, which tautomerizes and gives you this particular product. Now, if we try to understand the mechanism of Michael addition, and you can see this clearly as shown here, that in the first step we have taken this diethyl malonate as the example. When the ethoxide ion attacks as the base, it will take one of the proton of this active methylene group, and in turn there is a formation of this carbon ion. Now, this carbon ion in turn will be attacking on the beta carbon to the carbonyl of the conjugated carbonyl. So, this double bond is being attacked by this carbon ion at this beta position, and as a result we get this oxy anion. And further on, as this O minus will take the proton, you get this enol, and this enol will undergo tautomerization to eventually give you this product. So, you can see it is a very simple mechanism where the first step involves a proton abstraction by the base to yield the reactive intermediate, which is the enolate ion, and in the next step the nucleophilic enolate attacks the conjugated ketone at the electrophilic alkene carbon, thereby transferring the electrons to the electronegative oxygen, yielding an intermediate enolate adduct. Thus, the conjugate 1,4 addition occurs. And finally, the enolate product gets protonated by extracting a proton from the protic solvent or from the active methylene or during the acid workup, and this usually tautomerizes to the more stable keto form. Even though the presence of a protic solvent aids proton transfer steps shown in the mechanism, the protic solvents are not a necessary requirement for successful Michael addition reactions. The conjugate 1,4 addition product is thermodynamically controlled and takes place at relatively higher temperatures. On the other hand, a 1,2 addition is also possible, which is kinetically controlled and takes place at lower temperature, as you can see in this particular equation. Here, if you start with diethyl malonate, then when this is reacted with this conjugated ketone, then it will be giving this 1,2 addition product, which is the kinetic control. And here this you can see this O minus is in the workup taking this H plus and giving this addition product. Similarly, another case you can look is this example where this cyclohexenone is reacting with this Michael acceptor, where the double bond is joined to OMe and OLi, which are facilitating this attack, and in the presence of THF there will be combination of these, and you are having this 1,2 addition product at minus 78 degrees, almost around 88% in yield, although the 1,4 addition product as shown here is only 5%. But if the same reaction is done from 25 degrees centigrade to warm conditions, that is slightly higher temperature, then it is the reversal. You can see the 1,2 addition product is only 7% and 1,4 addition product is now 83% in yield. So, you can see that at higher heating there is the thermodynamic control and 1,4 addition is the major product, and at lower temperature it is the kinetic control which comes and 1,2 addition becomes the major product. Moving further, carbon ions are weak bases and they favor 1,4 addition. However, if we use strong bases like alkyl lithiums, the alkyl magnesium halides, that is Grignard, etc., they will give 1,2 addition, that is directly to the carbonyl bond, unless the carbonyl bond is or the carbonyl group is sterically hindered by large groups. It also must be noted that the product of Michael addition can also further act as a potential Michael donor, and hence the further reaction of the product donor further with the acceptor must be controlled, or else it will lead to polymerization. In the classical Michael reaction, the enolate formed as a product is much more basic than the other enolate, and as a result it is thus rapidly discharged by protonation by solvent, other proton donors, or by starting beta dicarbonyl compound. With unsymmetrical ketones, a mixture of regioisomeric enolates may be formed, resulting in a mixture of Michael adducts. Generally, the more substituted alpha carbon of Michael donor are involved in the addition to avoid the further reaction. And you can see here in this particular example, when this substituted cyclohexanone is reacted with this conjugated carbonyl where this phenyl group is there, then out of these two products the major is this one and the other is minor. So, this is clearly helping in one of the preferential attack over the other. So, as I told you, with unsymmetric ketones it is the mixture of regioisomeric enolates which may be formed, and generally the more substituted alpha carbon of Michael donor are involved in addition to avoid the further reaction. With beta-beta disubstituted acceptors, the rate of reaction is quite slow due to increased steric hindrance, as you can see in this particular example, that with doubly activated acceptors, that is having two strong electron withdrawing substituents, this will not be such a problem. And here you can see that this alkene is having both side substituents, and it will stop the further polymerization and further attack. When both the Michael donor as well as the acceptor groups are located within the same molecule, an intramolecular Michael addition can take place, and this you can see as shown here, that when you start with this particular molecule and this has both this carbonyl and COOET, and you can notice that this particular CH2 is acting as the active methylene, and this molecule also has this conjugated double bond where this is the 1,4 addition type of requirement which we want is there. So, when this is reacted with base like potassium carbonate in the presence of ethanol, then there will be formation of carbene ion at this position which attacks at the fourth, and you can see there will be new this 5-membered cyclic ring which will be getting formed, and it goes into giving you this particular product as shown here. Use of various other nucleophile like amines, you will call it azamichael, or sulfur, that is thiamichael, to form CN or CS bond respectively, have also been carried out as extension of Michael reaction or Michael addition. And you can see here as shown in this general equation that when you start with this amine, then this NH part will be the one which will be attacking, and here is the double bond joined to the electron withdrawing group which can act as Michael acceptor, and in the presence of appropriate basic medium, then there is a formation of this new CN bond in this case. And here you can see the yield is almost from 70 to 95%, where R represents here is the alkyl. Similarly, R1, R2, R3 are the alkyl or the hydrogen substituents. You have this EWG, it can be, that is the electron withdrawing group, can be the methyl ester or the methyl ketone or the cyano or the amido and so on. In place of enolates, enamines can also be used as Michael donors in a very similar manner. And when we use enamines, then this reaction is called as Stork-enamine reaction. So, you can see it is an extension of Michael addition only, and here it is represented. You can see that this is the enamine where the N is at the joint to this doubly bonded carbon, which is the requirement for this to be classified as enamine, and when this enamine is reacted with this conjugated carbonyl, you can see that the lone pair over the nitrogen will move, and the beta carbon here, again this particular carbon of the double bond will be attacking as carbanion to this beta carbon of the conjugated carbonyl system, and you get this intermediate. Furthermore, this O minus will make this go into C minus, which further will take the proton, or other way around, the O minus takes the proton and then further the tautomerization happen. You will be getting this particular aldehyde, substituted aldehyde as the product, and further when this is subjected to hydrolysis, then the C double bond N undergoes cleavage and you can get a carbonyl in place of this. You are already familiar that imines on hydrolysis will give you ketones. So, this is the imine hydrolysis which is being conducted in the last step, and that is how you can get this type of molecule via the Stork-enamine reaction. Let us now move to the asymmetric Michael addition. Recent research has focused on the asymmetric variant of the Michael reaction, which has not only expanded the scope of this classical reaction but also increased its utility for the synthesis of various natural products and compounds of pharmaceutical importance. So, there are essentially two major ways for obtaining a chiral Michael product. That is, first is the use of chiral substrate, and the second is the use of chiral catalyst. So, when we use the chiral substrate, that is, one can use a chiral Michael donor or a chiral Michael acceptor, or even a combination of both to get an adduct in which the substrate essentially controls its stereochemistry. For example, if we look at this equation here as shown, that we are taking the CH3NO2, which is not chiral, but when it is reacted with this chiral conjugated ester, where this ester is acting as electron withdrawing group to this double bond. So, in the presence of base, there will be generation of CH2 minus because nitro acting as electron withdrawing group. So, base will be taking this acidic hydrogen, and this CH2 minus NO2 will be attacking on this beta carbon to the ester, and what we get is this addition, which further on by working with acid you will be having this addition happening. The second way of introducing the chirality is the use of chiral catalyst, and when we do that, the use of chiral catalyst induces chirality in the reaction product. Let us see how. Of these, the use of chiral enamine catalyst has received great attention. Initially, stoichiometric amounts of catalyst were used, but now even 10 to 20% mole percentage or even less of the organocatalyst is sufficient to bring about a successful asymmetry. So, as you can see in this particular example, that almost 5 equivalents of the cyclohexanone we take, and we are doing the reaction with this conjugated phenyl system. You have the phenyl joined to the double bond, and another side you have the nitro. So, this doubly bonded system joined to phenyl and nitro acts as the Michael acceptor, and the cyclohexanone will act as the Michael donor. So, in the presence of DMF at room temperature, and when we take this chiral catalyst, this is the organocatalyst which is chiral, we get this particular Michael addition product which is 86% in yield, and if you look at the ratio of syn is to NT, it is 19:1, and almost it is 99% and higher enantiomeric excess that we get for this chiral product. The chiral catalyst may induce chirality in the substrate through various mechanisms. For example, use of chiral secondary amines, for example proline based organocatalyst, may lead to a chiral Michael adduct via 3 mechanisms. That is, the first mechanism is activation of the Michael acceptor via the formation of iminium species, which you can see as shown here in this first, that the nucleophile will be attacking at this position and then it undergoes the attack. The second plausible mechanism is that it may act as a base, forming a complex with enolate to react with the acceptor, and that is shown in this second structure. So, you can clearly see here, now it is the enolate which will be attacking to the Michael acceptor, and in the third plausible mechanism, it is the activation of ketone donors through the formation of an enamine intermediate, as it is shown in this third. So, here you can see this enamine will be attacking on this double bond via the C minus, and then you have the addition happening. Thus, in all these cases, there is a discrimination of attack by either the acceptor or donor towards one of the enantiomer phase of the chiral intermediate formed with the catalyst, which in turn results in the generation of asymmetric centers in the product. For example, the asymmetric Michael addition of aldehydes to nitrostyrenes was catalyzed by pyrrolidine sulfonamide catalyst, which exhibited excellent enantiomer selectivity, that is almost around 94 to 99% enantiomeric excess, and distereoselectivity greater than 20:1 diastereomeric ratio, and high yields of almost 63 to 99%, as you can see from this particular example. So, you can see here that this is the aldehyde where this R and CHO and the CH2 is the one which will be the attacking part, and it is reacted with this double bond joined to nitro and AR, and this AR and nitro will both being electron withdrawing will facilitate the attack of this here, and furthermore this is how the reaction is going to take place. So, there will be formation of this addition product which further undergoes the cyclization, and finally you have this particular product which is getting formed. So, as you can see in this equation shown here, initially the catalyst forms an enamine with the aldehyde, and due to which the nitrostyrene attacks favorably through one of the phases to form a most stable transition state, as shown here, in which the enamine and beta nitrostyrene are cofacial, with the nitro group hydrogen bonded to the protonated sulfonamide, and this subsequently leads to the product with the desired enantiomer selectivity. Other catalysts used for asymmetric Michael addition include organocatalysts such as chiral diamines, chiral crown ethers, chiral amino acids, chiral alkaloids, and chiral oxygenolines or heterogeneous catalysts like polymer supported catalysts, organometallic complexes, etc. So, after studying about the Michael addition, which is the conjugated addition, and it is a 1,4 addition we have seen, let us now move to the addition to cyclopropane rings. And you must be wondering, as I told you earlier also, that why a section on cyclopropane ring system has popped up while we are studying or discussing the addition reaction to CC multiple bonds. Actually, the cyclopropane ring system, although an alkane, shows reactivity akin to an alkene towards various electrophiles, nucleophiles or free radicals. And what is the reason for this type of reactivity of cyclopropane ring system? It can be explained by having a close observation on its structure and bonding properties. So, let us see the structure and bonding in cyclopropane ring. Cyclopropane has a triangular planar structure, due to which the bond angles between carbon-carbon bonds are expected to be 60 degrees. This is far less than the thermodynamically stable angle of 109.5 degrees as per the sp3 hybridization of the carbon atoms. And due to this, there is a considerable amount of ring strain in the cyclopropane molecule. This cyclopropane model here, you can see here these all angles, there is a 60 degree orientation because of this cyclo, a 3 point like a triangle, and this 60 degree is a deviation from the routine sp3 nature of the carbon, where it should have been 109 degrees 28 minutes or around 109.5 degrees. So, there is a strain which is there in this cyclopropane ring system. In addition to this angular strain, cyclopropane also suffers additional torsional strain. The torsional strain is due to the coplanar arrangement of the carbon atoms, wherein leading to the eclipse arrangement of the CH bonds. That eclipse arrangement you can clearly see here, that these hydrogens and these hydrogens and these hydrogens, it is the eclipsed, it is not staggered, and it is also visible if you look it from this side, that it is the eclipsing conformation for these hydrogens which are attached to these carbons in this cyclopropane ring. Important characteristics of cyclopropane, let us discuss them also. The CC bonds are shorter than in alkanes, that is in cycloalkane we have 1.51 Armstrong as compared to 1.54 Armstrong for alkanes. The HCH angle when it is opened up, it is 115 Armstrong versus the 106 Armstrong in propane. The CH bonds are more acidic in cyclopropane as compared to propane. The strain energy is 27.5 kilocalories per mole. The CC bond strength in cyclopropane is considerably weaker, that is 65 kilocalories per mole, than for a typical CC bond, which is around 80 to 85 kilocalories per mole. It has been suggested that significant rehybridization occurs in cyclopropane and bonding between the carbon centers occurs in terms of bent bonds. That is, this was given by Coulson and Mohit as Coulson-Mohit model, wherein the carbon-carbon bonds are bent towards outside so that the interorbital angle is 104 degrees, which consequently reduces the level of bond strain, because had it been 60 degree, then it would have been even a larger strain. So, it is the intermediate between the sigma and pi bonding. These bonds are also sometimes called as banana bonds, and as you can see in this figure shown here, these are depicting the banana. So, rather than a straight overlap, these are now protruding or going towards outside and giving you the banana bonds type of structure. Thus, the CC bonds have more P character than normal, while the CH bonds have more S character, and thus it can be seen that ring string substantially weakens the CC bonds of the cyclopropane ring, and hence we can say the cyclopropane is much more reactive than alkanes or other higher ring systems. So, you can see here in this Coulson-Mohit model that although the internuclear angle is 60 degrees, but because of the banana bond, these orbitals are protruding outside, the interorbital angle is around 105 degrees, and because of that there is the strain is slightly reduced, but there is still considerable strain, and that is why it will be undergoing the addition reaction to release that strain. Then there is another Walsh model which is shown here, and this another Walsh model is based on the molecular orbital consideration, envisions the cyclopropane as being constructed from 3 sp2 hybridized methylenes, that is CH2. 2 of these sp2 orbitals are used for the CH bonds, and one forms an inner 2 electron 3 center sigma bond, leaving the p orbitals to form some kind of degenerate pi-like orbitals. So, thus this Walsh cyclopropane model has considerable sp2 character, and according to this it should react in analogy to olefins or alkenes. This figure you can clearly see, it shows the molecular orbital diagram for cyclopropane as formed up by 3 methylenes in the increasing order of energy. So, as an outcome of this structure, whether it is the Coulson-Mohit model or the Walsh model, one thing is very clear, that there is considerable strain and there is pi character or more p character which is there in these carbon-carbon bond, and because of this the cyclopropane undergoes addition reaction. So let us discuss the addition reactions of cyclopropane ring. So it has become now very clear that cyclopropane ring system suffers from a large ring strain, that is, which is a combination of angular strain and torsional strain, and leads to significant weakening of the CC bond. Thus CC bond shows a greater P character while the CH bonds have more S character. Thus in effect cyclopropane ring undergoes any such reaction which can subsequently help in relieving the ring strain. And most of these reactions are similar to those of alkenes, and most common of these are addition reactions. That is, they can be electrophilic, nucleophilic or free radical, which lead to opening of the ring, which illustrate some of the addition reactions of cyclopropane. You can see when you have cyclopropane reacted with hydrogen nickel, then this undergoes cleavage and there will be addition of H and H across one of this bond and you get normal propane. When this is reacted with HBr, just like propene reacts with HBr, but that will be between those two carbons, here it will be by breaking off and it will be at first and third carbons, that there will be addition of H and Br and you get this bromopropane as a product. Similarly, like you have alkenes reacting with water and acid giving you alcohols, here also in cyclopropane just add H and OH across the propane and you get the propanol as the product. And if you do the reaction with chlorine FeCl3, then there will be formation of 1,3-dichloro, or if you do the reaction with bromine FeBr3 or similar other Lewis acid, then there will be formation of 1,3-dibromo addition product, that is 1,3-dibromopropane. Now in each of these reactions, a CC bond is broken leading to ring fission and the atoms of the reagent attached at two terminals of the resulting propane chain. Depending upon the substitution of cyclopropane ring, which can be electron donors or acceptors, any of its three bonds are likely to undergo cleavage. The reagent must be able to polarize itself into nucleophilic and electrophilic centers for the subsequent addition to occur. And this is as shown, and note that this is not the full mechanism. So here the propylene reacts more readily with bromine or chlorine, while for reaction with cyclopropane a Lewis acid is required, that is FeCl3 or FeBr3, to effect the sufficient polarization of the chlorine or bromine molecule, because in case of alkenes the alkene will be polarizing, but cyclopropane being non-polar it will not be able to polarize. So you have to give the polarization to the reagent molecule and that is how the reaction will be happening. So as shown here in these two general additions shown, there is X minus and Y plus as the reagent adding, and Y plus attacks on one carbon and then followed by X minus on the other, you get the addition product. Similarly here one of these will be attacking to first carbon and relatively to the third carbon the other will be attacking. So you have the X minus and Y plus adding. So you can compare the alkene and the cyclopropane addition, there you get 1,2 addition product, but here you are getting the 1,3 addition product, which is very obvious. Now let us continue our study and move to the mechanism of electrophilic addition to cyclopropane. And before discussing the mechanism, there are two important points to be noted for addition reaction of cyclopropane. First is that the mechanism must be stepwise, as reaction of D2SO4 with cyclopropane yields along with the expected product minor amounts of two more products, that is second and third, as shown here. So you can notice that this first one is the expected product where D and SO3 D will be adding to the first and third carbon, but in contrast there is 1,2 addition product, that is the second one, and there is 1,1 addition product also, which is third. Another point that you have to keep in mind is the electrophilic addition in substituted cyclopropanes generally follows Markovnikov's rule, wherein hydrogen adds to the carbon which already has more number of hydrogens. That is, as shown here, that if you have a substituted cyclopropane, one carbon is having one methyl group and the other carbon is having two methyl substituents, and if we are adding HBr, then out of these two carbons, that is the hydrogen will go to this carbon and Br will go to this particular carbon, and thereby you will get this particular product. So this suggests that the mechanism comprises of an initial attack by an electrophile, for example H plus, on the ring carbon with the most hydrogens, generating a positive charge on the carbon as a carbocation, and this positive charge may be then transferred to the other carbon of the ring via the rearrangement, and then the most favorable intermediate would be the one in which the positive charge is on the most substituted carbon, that is the most stable carbocation. And this cation is subsequently trapped by its reaction with the nucleophile, as you can see in this particular mechanism shown. You are starting with cyclopropane, where this particular carbon has the alkyl substituent. So when it is attacked by H plus, you get this carbocation, or you get this possible carbocation or this, and out of these you can see that this is the most stable one, and it will be X minus will be attacking to that position where it is the most stable carbocation. There is another type of mechanism which has been suggested, and it depicts an edge protonated cyclopropane, and this is shown as here, that is starting with this substituted cyclopropane, the H plus will be attacking, and the H plus attacks from the edge, so it is outside, and then the X minus attacks, and then finally this H gets shifted to the other, and this mechanism you can see will be justifying more for the 1,3 type of addition which is happening. Now let us discuss the nucleophilic addition happening to cyclopropane. Now this is a contrast as compared to alkenes. Alkenes undergo electrophilic addition, not the nucleophilic, but cyclopropane will be undergoing nucleophilic addition as well. The ring fission of cyclopropane by nucleophiles is possible only when an electron withdrawing group is present on the ring. So this electron withdrawing group, like you can see here, is being represented by W. It will make the cyclopropane ring have electron deficiency, and that is how this nucleophile can attack at this particular relatively the second position carbon to this W group, and as this attacks here, there will be cleavage of this CC bond of the cyclopropane, and you get this carbanion which is later attacked by H plus, and eventually you have the nucleophilic addition happening. This reaction has been widely used in organic synthesis and can be used as a homologous variant to a Michael type addition to generate a 5-membered ring. So as you can see in this reaction shown here, that there is a cyclopropane joined to 2 esters, and both these ester groups will be helping the nucleophilic addition as they are electron withdrawing, and when this reacted with diethyl malonate, this methylene, the CH2 in between, in the presence of base, you can generate this carbanion, and this will be attacking as a nucleophile to this particular carbon, and then this bond breaks and there will be formation of this carbanion. And once we get this carbanion, there can be another attack, because now this will attack as a nucleophile, and this ester this carbon will be electron deficient, thereby you will get this alkoxide ion, and in this alkoxide ion this OET will be going out as a good leaving group, thereby giving you this particular keto in this particular position, and furthermore there will be in the presence of basic medium another carbanion generated, because this CH2 is in between these two electron withdrawings, this CO and COOET, and this will be further when you work up with proton will be giving you this particular product. So you can see that this O minus will make this OET minus go as a good leaving group, so ethoxide ion goes out, and as a result you have this keto group arising here, and this keto ester, you can see this is a 5-membered cyclic ring having 3 ester substituents and 1 keto, and because the medium is basic, there may be further generation of this carbanion, but then finally when you work it up with the help of acid, then it will be giving you the neutral 5-membered product. So let us now move to the addition of free radicals to cyclopropane. So cyclopropane can undergo additions to electrophilic reagents, to nucleophilic reagents, and now we will discuss about the free radical addition. Free radicals add to the cyclopropane ring system easily. For example, bromine can add to cyclopropane ring in the presence of UV light via a free radical mechanism. So in this mechanism, initially the Br free radical, which is formed with the help of UV light and bromine. So this Br dot will attack the least hindered carbon to yield the most stable free radical, and then this so formed free radical will be taking another Br dot from another bromine molecule, and another Br dot will be generated and you get this addition product. This Br dot in turn will be attacking more and more cyclopropane molecules. So that is how, like you are already familiar with the chain initiation, propagation and termination. So similarly here also that can be envisaged. We have first of all learnt about the Michael conjugated addition in detail, and then later on about the cyclopropane addition. The Michael reaction, if we talk about, is essentially a 1,4 conjugate addition and is one of the most powerful carbon-carbon bond forming reactions in organic synthesis. Both the Michael donor and Michael acceptors have activating group, that is electron withdrawing in nature, that can also serve as point for further functionalization. In place of enolates, enamines can also be used as Michael donors, and when we do so, this is called as Stork-enamine reaction. The mechanism of Michael reaction involves proton abstraction from the Michael donor, resulting in a stable carbon ion, and conjugate 1,4 addition with the Michael acceptor molecule, followed by subsequent proton abstraction and then eventually tautomerization to yield the stable Michael product. We have also studied that various catalysts have been used for the asymmetric Michael addition, which has expanded the scope of this classical reaction. And moving to cyclopropane, we have seen the cyclopropane ring system suffers from a large ring strain, which is combination of the angle strain and torsional strain, and this leads to a significant weakening of the CC bond and more p character in the CC bond. Various models for the structure and bonding of cyclopropane we have seen and are suggested, and out of these the Coulson, Moffat and Walsh model we have discussed. Cyclopropane undergoes many reactions similar to those of alkenes such as electrophilic, nucleophilic as well as free radical additions, and we have considered some examples around this. And you should remember that the electrophilic addition to cyclopropane follows the Markovnikov's rule. So if you have a substituted cyclopropane, you can find out the major product keeping in mind the Markovnikov's rule.